in the past you've studied just waves kind of in general, so we were able to skip over a big chunk of review stuff just because it's something that, has been drilled into you from a very young age, and it's something that's not, you know, too difficult to get the grasp of. So we could jump right into talking about our next unit, which is optics. So we are going to be looking at a special case of waves, which are electromagnetic waves. So it kind of leads in from that last unit that we had, um, which was electromagnetic induction. So electromagnetic waves are, first of all, they're transverse waves. So remember that transverse means well, the wave, let's say, vibrates perpendicularly to the direction that it propagates, to the direction. So that just means that, if it's moving off to the right, then it's vibrating up and down, or I guess back and forth in the other plane if you want to look at it that way. Alright, so transverse waves that are produced by the oscillations of magnetic and electric fields. So we talked about that a little bit before. It's just you have some electric field that generates a magnetic field, and that magnetic field generates another electric field, and it just goes back and forth and back and forth. Alright, so transverse waves are the electromagnetic waves are a little different than things like sound waves because they don't require any medium, which means they are non-mechanical. So mechanical waves have to have some kind of stuff that they can travel through. So these EM waves are non-mechanical. So that means that they can travel through a vacuum, like space, and they're able to give us some information about things that, are beyond the atmosphere. So things that, it would have to travel through a vacuum to get to. Aside from, gathering information from other parts of the universe, they play roles in so many different parts of our lives. So you could use a microwave to heat up some dinner. Radio waves are electromagnetic waves. An X-ray, if you've ever had one of those, I've had plenty. Um, and, just seeing in general, that comes from visible light waves. So we're going to focus a little bit on that first, or that last example, the visible spectrum, when we talk about optics. Optics is a study of visible light, things that we can see, and how can it be manipulated to produce images that we're able to see. So we said before, electromagnetic waves are able to travel through a vacuum, and when they're moving through a vacuum, they do so at the speed of light. So regardless of whether it's a ultraviolet wave, a radio wave, any kind of wave, electromagnetic wave, when it's in a vacuum, will travel at the speed of light. I can't remember exactly which value the sheet uses, but I'm going to use 2.99 times 10 to the 8th meters per second. Um, the sheet might round it to 3. They tend to do things so that it's a little bit easier to do mental math, and you'll be fine if you use 3, but a little more precise. And it's going to be represented by the variable c. So c is a constant, just like you had. G is always 9.81 meters per second squared. C, lowercase c, anytime you see it, you can pretty much be guaranteed that it'll mean 2.99 times 10 to the 8th meters per second. So we'll see in this unit and later on when we talk about modern and relativity that this is the fastest speed that there is. Nothing can ever go any faster than light, and we'll have some mind-blowing discussions when we get to um, the modern unit and we're talking about relativity. It gets kind of neat. But anything faster than that, it's only purely theoretical and all speculation. Nothing that's ever been observed or proven or even close to being replicated. So because the speed of electromagnetic waves is constant, we're able to calculate the frequency if we know wavelength and vice versa. So F for frequency is equal to C divided by lambda. So F would be your frequency in hertz. Oh, jeez. Um, C is, of course, the speed of light. And our lambda is equal to wavelength in meters. So if we actually wanted to calculate this, so F equals, we know for speed of light we can use 2.99 times 10 to the 8th meters per second. Divide that by, let's say we have a wavelength that is 6 times 10 to the minus 7 meters. Then our frequency there would be 5 times 10 to the 14 hertz. So wavelength and frequency are really the only qualities that electromagnetic waves can have that distinguish them from one another. Um, some things are really, really dangerous, like ultraviolet rays, X-rays, gamma rays, whereas on the other end you have radio waves that aren't quite as dangerous as the others. So as a result of all these differences based on frequency and wavelength, we can list all the kinds of E&M waves on just a one-dimensional graph, and we call it the electromagnetic spectrum, so a range of all the different types of electromagnetic waves. And there's a picture of it just down here. Alright, so you can see that the frequency goes along the top, the wavelength goes along the bottom. So if we go from left to right, frequency increases. So radio waves would have the lowest frequency, then micro, which we were wrong about when we were doing our quick little review in class. Infrared, visible, ultraviolet, X-rays, gamma rays, they all have an increasing frequency, so more events occurring per second. If you look at the wavelength across the bottom, the wavelength decreases as you go from left to right. So you start out at about 1 meter wavelength for radio waves, and they get smaller and smaller and smaller, all the way up until 10 to the minus 12 for gamma rays, which should make sense. If they're a lot more cramped together, then you should have a lot more passing through if they're all moving at the same speed. I'm going to try to remember what that, I don't even know what it's called now. Oh, a mnemonic. I used to have a mnemonic for remembering the order of the electromagnetic spectrum, and I just can't remember what it was. I guess maybe it wasn't that good. Alright, so a higher frequency and the shorter wavelength corresponds to a wave with, you can definitely tell the more dangerous ones are up on the right end. So higher frequency Shorter wavelength, way, way, way more energy than something that is the opposite. So even though all the waves are traveling at the same speed, the ones that have a higher frequency are oscillating a lot faster. So the direction of propagation is the speed, that's the speed that it's traveling at. And then the oscillations happen really quickly in a totally perpendicular direction. So that's how they're able to all have the same speed. And just, that oscillation, how big, how fast, that is where all the energy is associated with these traveling waves. Um, Visible light, the one that we can see, that's the part of the electromagnetic spectrum right here, right in the middle of those short bands that are all very slim and close together. Um, that occurs between roughly 10 to the minus 6 and 10 to the minus 7 nanometers. Oh, I guess that'd just be meters. 10 to the minus 6 and 10 to the minus 7 meters. Get rid of that. You might want to cross that part out to not confuse yourself. So these are these E&M waves with these specific wavelengths that come from the sun, from light bulbs, from your television screen, from your cell phone screen, all these different sources. Those are the ones that strike at the back of our eye and transfers the energy electrically to our brain, and we're able to perceive each certain amount of energy as a different color.